In this lecture, we are going to go over limits. So what are limits? Again, you start from a function f. So having a function f, you look at somewhere, some value in its domain. As x is closer and closer to this number a in the domain of f, you want to track how the value of f changes. So essentially, if the value of f is y coordinate and you are changing your x coordinate and see how the y coordinate changes. Okay, if somehow as x gets closer and closer to the number, somehow the y coordinate also gets closer to a number, that's the limit. Sometimes the y coordinate just goes to become bigger and bigger, or smaller and smaller. That's where you get positive infinity or sometimes negative infinity as the limit. Similarly, you can do the other way around. You let your x, instead of approaching a number, you let your x goes to gets larger and larger. So as you let your x goes to infinity, then the y coordinate could settle at some point, like gets closer and closer to a number, that's your L. And similarly, of course, you can make, x approaches negative infinity, or as x approaches infinity, f of x also goes to infinity, right? So pretty much for x value, it can goes to a particular number, it can goes to positive infinity, it can goes to negative infinity. Also, we have single side limits that I didn't really include here, which are as x approaches a number only from the higher side, but the positive side, or x approaches the number only from the negative side. Okay, although of course you can read the definition, but pretty much that's what it is. For example, we say the limit of f of x approaches L as x approaches A if we can make the values of f arbitrarily close to L by restricting x to be sufficiently close to A on either side of A, but not equal to A. Well, this definition is more like describing the the precise definition in a sort of vague language. But remember, the limit only happens around the number. We don't really care what happens at the number. And we say a function is continuous at a particular number in its domain, again at A, if f of x approaches f of A as x approaches A. So what it really says is, as your, say this is A, so as your x value gets closer and closer to A, your function somehow has to settle somewhere, like, so here you go. Pretty much this little piece has to be a piece. That's why it's continuous. Well, pretty much here, the functions that we know are continuous on its domain. Polynomials, rational functions, root functions, trigonometric functions, exponential functions, logarithmic functions, hyperbolic functions. So again, every function that we know are continuous in its domain. For example, can use f of x equals 1 over x. The domain is, x not equal to 0. So if you look at its curve, it's continuous everywhere but 0, because 0 is not in the domain. So, again, the functions that we know essentially is if you're in the domain. If the value is in the domain, the function is continuous. So what this gives us is, when you are computing a limit of a function, pretty much all you need to do is plug in the function. So plug in the limit in the function. If it works out, which means the number is in the domain of the function, then there you go. You are having the limit. Now let's see examples. We are looking for their limits. Of course, there is a possibility limits do not exist. But if it does, we need to compute it. So the first example, the limit of e to the 2x minus cosine x as x approaches 0. Well, when you are computing a limit, always plug in the number first. So this will be e2 times 0 minus cosine 0, and this, work it out, that's 0 minus cosine 0 is 1, so e negative 1. It is a number, which means 0, when you plug in 0 in the function f of x equals e to the 2x minus cosine x, 0 works out. That means 0 is in the domain of f. Then the limit will be the value of the function. Look at second example, the limit as x approaches negative 1 of x plus 3 over x plus 1. Again, the first thing you plug in, you will have negative 1 plus 3 over negative 1 plus 1. And here you go, you get 2 over 0. This is not a number, not a real number. That means negative 1 is not in the domain of the function x plus 3 over x plus 1. So plug-in doesn't work. Then you need to start over. Think about it. There are many ways you can do it. You can graph the function. You can sort of see how the function, how the value changes as x approaches negative 1. So if I let my x goes to negative 1 from the positive side, the value would be negative 1 plus 3, right? When x approaches negative 1 from positive side, the numerator is still 2, but the denominator will be, when your x is close to negative 1 but a little bit above negative 1, you are going to get a number that is close to 0 but positive. I'll write 0 plus, meaning it's a very small number that is positive. So you are getting 2 over 0 plus, which means it's 2. Numerator is fine. It's definitely 2 over a very small positive number, and that's where you are going to get infinity. But on the other hand, when you let x approaches negative 1 from the negative side, so x is less than negative 1, but getting closer. This, if you plug in, it will be negative 1 plus 3 for the numerator as well, but on the denominator, it will be negative 1 plus 1, 0, but this time is a little negative number. So 2 over 0 negative, and this is negative infinity. The limit as x approaches negative 1 from positive side and negative side are not the same. They're both infinity, but they are not really the same. So the limit does not exist. I mean, even if the limit is infinity, technically the limit does not exist, but the limit is an infinity, right? Here it's not exist, it doesn't exist, and it's not even an infinity. L'Hopital's rule. So when we are having a case like the previous case where you have a zero denominator, you can't just do plug in. But if somehow you also have a zero numerator, that's where you get indeterminate form. Indeterminate form are 0 over 0 or infinity over infinity for fractions. There are other indeterminate form, but L'Hopital's rule only work with quotients, with 0 over 0 or infinity over infinity. If that's the case, you can just differentiate the numerator and the denominator separately the limit of f over g will be the same as the limit of f prime over g prime. Okay, and also this works not only that the right hand side, the quotient, after you differentiate, the quotient of the derivatives, if you plug in, is a number. It also works when it's infinity, positive or negative. And here several things I put in the remark. First, x approaches a doesn't have to be a. It could be a from positive side, a from negative side, x approaches positive infinity or negative infinity. And again, I'm here, second is to emphasize that L'Hopital's rule only work when f over g is an indeterminate form. When it's not a 0 over 0 or infinity over infinity case, you can't do that. Okay, and then third, I'm trying to say that, as x approaches infinity, when x, goes higher and higher, we sort of know which function grows faster. So x approaches infinity, log x goes to infinity slower than a power of x, whatever a is. And then, of course, a is positive here. And then x to the a's power, power function goes slower than exponential function with base e, or again, any positive base greater than 1. Not just positive, we need greater than 1. Okay, so very, very importantly, the second rule. That's why every time before you use L'Hopital's rule, you need to make sure that I'm having a 0 over 0, or I'm having an infinity over infinity. Otherwise, you can't use the rule. Okay. For example, the case that the function that we just talked about, the limit as x approaches negative 1, x plus 3 over x plus 1. If you don't check L'Hopital's rule and just do the differentiation, it will be 1 over 1, which is 1, and we already work it out. The limit does not exist. Why was that? Because it's 2 over 0, not 0 over 0. Okay, you are not having the indeterminate form. You have a form that you can determine that it goes to infinity, just on different side it goes to different infinities. Okay, so make sure you are having 0 over 0. Which form you are having? Are you having 0 over 0 or infinity over infinity? Do the plugin, see whichever you have, but write it down. I'm having 0 over 0, so I'm applying L'Hopital's rule. Or similarly, I'm having infinity over infinity, so I can apply the L'Hopital's rule. You need to know which form you are dealing with, because that's like making sure you are checking it. Now let's see examples. These three examples are pretty much the same function, x squared minus 4 over x squared minus 5x plus 6, but I'm letting x approach different numbers. So let's see each of them. The first one, as x approaches 2, what's the limit? 2 squared minus 4 over 2 squared minus 5 times 2 plus 6. This is really 0, 4 minus 10 plus 6 over 0. So you are having 0 over 0 case. That's why you can, let me just move it a little bit lower. So you can just say this is the same as the numerator taking derivative over the denominator taking derivative. So this is the limit as x approaches 2, 2x on the top, 2x minus 5 on the bottom. Plug in 2 again. 2 times 2, 2 times 2 minus 5. Yes, we are going to have a number which is 4 over 4 minus 5, 4 over negative 1, which will be negative 4. Okay, so again, the thing is that you need to make sure you know it's an indeterminate form of 0 over 0 to apply the L'Hopital's rule and do the differentiation of the numerator and denominator separately. Second example, I'm having 4 squared minus 4 over 4 squared minus 5 times 4 plus 6. This is 4 squared 16 minus 4, 12. Actually, I can stop here. I need 0 over 0 or infinity over infinity. Apparently, this is neither. But I'll finish the denominator because 16 minus 20 plus 6. Well, it's not L'Hopital's rule. Plugging in, that's better. You don't have L'Hopital's rule. That means this is your limit. And this is 12 over 22 minus 22, so which is 6. Okay, so here you always plug in and see what happens. If it works, it works. If it doesn't work, you will see is it a 0 over 0 infinity over infinity case. The third one, x approaches infinity. So this one you can't really plug in. It's infinity anyway. So when x approaches infinity, the numerator x squared is infinity. The denominator polynomial with positive first term is also infinity, positive infinity. So you are having infinity over infinity. That means you can use L'Hopital's rule. X squared over 4, taking derivative x squared minus 5x plus 6. Taking derivative, you are going to have the same function as the first example, 2x over 2x minus 5. But this time, you are having x approaches infinity. So plug in again. This is your new function. 2x infinity, 2x minus 5 infinity. Another round of L'Hopital's rule says I'm going to take derivative of 2x and I'm going to take derivative of 2x minus 5. And that just gives me 2 over 2. Well, now it doesn't really depend on x anymore. It's 1. Well, if you want to, is 1 as x approaches infinity. X doesn't show up in the function f, so it's just 1. So here I want you to see that with the same function, when your x approaches different point or different value, of course the limits are different, but also here you can see we applied the L'Hopital's rule only once. In first example, we didn't use L'Hopital's rule at all in the second example, and we used L'Hopital's rule twice in the third. So here, just remember every time before you use L'Hopital's rule, you were given a limit of quotients, or you somehow get or you get a new quotient from L'Hopital's rule. Plug in. Now you can pause the video and try practice number 1 through number 4. After knowing what limits are, we can talk about improper integrals, which are integrals with upper limit or lower limit or both limits as infinities. So pretty much, wherever you have infinity, you are really having a limit of that particular limit, upper or lower. Okay, I'm talking about these two numbers. That's supposed to be a and b, right, in general. If one of them is replaced by infinity, we're saying that number called t goes to infinity. So, and then you take the limit. But anyway, I have the definition here. If the integral of f of x dx exists for every, from the lower limit a to upper limit t, for every t greater than a, then you can let a goes to infinity, upper limit goes to infinity, and say the integral of a to infinity f of x dx is, well, pretty much you just let the upper limit t goes to infinity, and for each of the different t, you get a different integral. different values. Okay, if the limit exists, the integral convergent. If the limit does not exist, the integral is divergent. And sometimes the limit does not exist because it's not a certain number, like it changes. Sometimes it's not, the limit does not exist because it goes to positive or negative infinity. So when you know that it goes to infinity, well, you still need to say it goes to infinity, positive or negative. Anyway, let's see examples. We want to know whether the integral is convergent or divergent. And if it is convergent, find its value. So by definition, we know that the limit as t approaches infinity, 1t, you just replace that infinity by t and let t goes to the infinity. This is x negative 2 dx. Well, forget about the limit. This is just a regular integral with, of course, the upper bound is not a number, but t, pretend it's a number. So at this moment, you just carry the limit but work out the integral. This equals the limit as t approaches infinity. We don't really touch that. You can do the antiderivative x negative 2. You add the power by 1, which will be negative 1. Then you flip it. Then it's a definite integral from 1 to t. So this is the limit as x approaches infinity, negative 1 over x. It's negative x to negative 1 power, so 1 over x from 1 to t. Now I can plug in the two limits. So this is negative 1 over t minus negative 1 over 1. Oh, sorry, t approaches infinity. So this is the limit as t approaches infinity, negative 1 over t. Negative and negative becomes positive, plus 1. And of course, when t approaches infinity, negative 1 over t is negative 1 over a large number that's 0. So this is really 0 plus 1, which is 1. So it is convergent, and it convergent to 1. The integral is 1. Next example, if I have the same, integral 1 to infinity, but this time instead of having 1 over x squared, I'm having 1 over x 1/2 power. Pretty much same thing. And by the way, you don't have to really say the limit as t approaches infinity from the very beginning. You can do the t approaches infinity when you really finally touch the infinity. You need to plug it in. That's where you need to write it out as what it means. Before that, actually, you can simply say, okay, it's 1 to infinity x to negative 1/2 dx. I am going to do the antiderivative. Negative 1/2 plus 1 will be positive 1/2, and I flip that. I'm still evaluating from 1 to infinity. I know technically the writing is not precise, but again, you don't have to write the limit t approaches infinity and then write a t on the upper limit. You do that when you really need to change that number or plug in that number, which is almost now. So we found its antiderivative 2x 1/2. This is where I'm going to plug in, right? Next step. And this is where I'm going to say, okay, that is t approaches infinity to, do I want to say radical? Yeah, radical x from 1 to t. And that is the limit as t approaches infinity to radical t minus 2 radical 1. And that is the limit as t approaches infinity to radical t minus 2 times 1, which is 2. And, As t approaches infinity, radical t approaches infinity, 2 times radical t still approaches infinity, minus 2 and infinity minus 2 is still infinity. So the integral is divergent, but it diverged to infinity. If you compare these two cases, when you are having an integral of a negative power of x, 1 over xp, okay, so I wrote it as reciprocal from 1 to infinity, actually from any number to infinity, as long as the lower limit is positive. 0 is not in the domain, so it can't go negative. And a to infinity, actually in general, but anyway here, 1 to infinity for our purpose later. If p is greater than 1, like our 2, the first example, the integral is convergent, but when p is less than 1, less than or equal to 1 actually, but of course here we're talking about greater than 0, okay? Well, not necessarily if it's negative you are taking an integral of a positive power of x, which still will be divergent anyway. But yeah, I don't think that's worth noting. Anyway, when p is less than or equal to 1, the integral of 1 over xp is divergent. Say 1/2 is less than 1. It ends up with to infinity, divergent. Okay, now you can finish the practice. Number 5.